Hey there! In our last video, we compared deductive and inductive methods of reasoning and looked at the difference between top-down and ground-up logic. Deduction, we learned, was great for creating certainty, but making a valid statement didn't necessarily mean that it was true. In this video, we'll talk about two different methods of ground-up reasoning called inductive and abductive reasoning and some simple ways of thinking through the quality of their arguments. With induction, the conclusion you draw is called an inference, and this kind of logic the philosopher Karl Popper referred to as an inference by bucket. The other kind, abductive, leads to a conclusion called a hypothesis, which Karl Popper referred to as a searchlight. By the way, Popper had really strong opinions on buckets and searchlights, but we're not going to go into that too much today. Okay, let's start with induction. If you remember, induction is the ground-up method of logic where you start with your observations or evidence and use them to draw a general conclusion. With induction, your observations come in two different flavors, either by starting with raw numbers or data, which is called enumeration, or with varieties of information called elimination. The conclusion that you draw from the process is called an inference, and the process of imagination that moves you from observation to big idea is called an inductive leap. Little leaps are so reasonable, it's hard to find a reason for them to be wrong. While big leaps of imagination feel impossible to make. It's too far-fetched. Your leap of imagination becomes a leap of faith. In short, the smaller the leap of imagination, the stronger your claim is. The strongest inferences are the ones that are so easy to imagine that it seems unthinkable that they could be false. If this sounds familiar, sort of like science, well, it should. The empirical method is actually a strict process of doing and redoing inductive logic in a way that can shrink the inductive leap as close to zero as possible. The scientific method involves strictly controlled tests of observations based on hypotheses that can be used to formulate a more general conclusion. It's basically induction and abduction on overdrive. Okay, so let's talk methods. We'll start with enumeration, which is the simplest of the inferential methods. With this method, you take a lot of identical observations and draw an inference based on the data you get. With enumeration, it's the larger number of instances that strengthens your argument. This is like the experiment and repeatability portion of the scientific method. The more times the same experiment can be successfully done, the more seriously you can trust the result. Okay, so let's have an example. Let's say your aunt has one of those nondescript bowls full of leftover Halloween candy on the table and she offers you some. So you grab a handful, pop it in your mouth, and oh, gross, it's licorice. And then the next time you visit, she offers you candy again, and oh, gross, it's licorice again. Okay, so here's the deal. When you visit her again, do you start turning down your aunt's candy? Is twice enough, or do you need to try more to know for sure? Let's say that on your third visit, you refuse, but your sister says yes and gets peanut butter cups. In this case, you decided to make a decision based on a bucket with only two pieces of evidence in it. When your logic is based on gathering as much evidence as possible, you need to make sure that your bucket, your proof, is full of multiple trials to increase the likelihood that you're actually right. That does it for enumeration. Let's take a look at elimination next. This is also a type of method where you fill up a bucket, but instead of filling it with lots of the same thing like you did before, you get the same data from a broad variety of different things. For instance, if you want to understand if your aunt's love of licorice is weird or not, you can't just ask her the same question 100 times and see if she changes her mind. You have to ask lots of people the same thing to understand that. With elimination, the idea is to see how many different types or scenarios can support your inference. If you want to think about elimination being more like a Pokédex, I won't stop you. The more varieties of Pokemon you can gather in your Pokédex, the more effective it becomes. Gotta catch them all. Okay, let's have an example of what elimination works like. Let's say that you start wondering who these weird people are who actually like licorice. Surely there can't be that many, right? So you ask all your friends and family whether or not they like the taste of licorice, and you find out that 34 hate it, but 23 actually like it, and 2 of them eat it all the time, and 1 is your own mother. That's like 40% of the people you know. Whoa. So when you evaluate your bucket using elimination, you have to ask, how much variety do I have in my bucket? Do I have data from a robust number of things? Is it enough to be considered a representative sample, and was my sampling really broad? So thinking back to inference and buckets in general, you definitely want to see how much is in your bucket, but you also want to check around your bucket to see what didn't fit. If there's a lot lying around the bucket that you didn't put in there, you might be cherry picking your data. And you always want to ask, what kind of evidence might break my bucket, and does that evidence exist? Also, you always want to consider what other buckets are out there that might actually fit more data than yours. Okay, now that we've covered inference, let's talk about one more kind of reasoning besides deductive and inductive. Let's say that your aunt places that bowl of candy on the table in front of you and it's full of licorice. How would you explain why she does this? So you come up with a list of possible explanations and narrow down the field by seeing how well that explanation can also fit other things. For instance, with the first one, you remember how much your aunt likes the taste of perfectly normal things like peanut butter cups and chocolate. So it doesn't seem right that she has no sense of taste. As for her actually liking licorice, you also notice that she doesn't eat any of the candy herself, and she didn't eat any of the licorice jelly beans when the 2 of you raided your parents' candy stash that one time. So number 2 doesn't seem right either. And the more you think about it, your aunt really does like you a lot, so the third one doesn't explain anything else either. But the fourth option? It would explain when, after your cousin went to Sweden for vacation and brought back everybody candy as gifts, your aunt didn't seem all that excited about it. It would also explain the gift bag you saw in the trash. So out of the possible explanations then, the last one seems the most likely. She was hoping you'd eat it. Sorry, Auntie, no chance. Inference's offshoot abduction gives explanations. It's more like a searchlight. You understand what underlies the patterns you see or don't see in your observations. Hypothesis is more interested in determining causes, patterns, and connections. Like a good lamp, a hypothesis illuminates everything around it and makes your little corner of the universe a little less random. It helps you separate the signal from the noise. This is why Karl Popper called abduction the searchlight method. The way it works is that you start with a set of observations and you devise a hypothesis or theory that explains why your observations behave the way they do. The better your hypothesis is, the more observations it's able to explain. Some searchlights are so bright that they seem to explain life, the universe, everything. But others? The light doesn't travel far and it collapses under analysis. Most major scientific principles, like evolutionary descent or the model of the atom or gravity in space-time, start as hypotheses. Take gravitation, for example. The old folk tale is that Newton first started working on universal gravitation after noticing the apples in his garden always fell perpendicularly to the ground. His wasn't the first model to hypothesize why things fell, but his was the first one that really worked well beyond its original use case to explain the orbits of planets, and eventually predicting the existence of the planet Neptune. Newton's classical mechanics were the brightest searchlight in the room for a long time until it ran into something it couldn't illuminate: Mercury's weird, wobbly orbit. Newton's hypothesis said it wasn't supposed to oscillate, but Mercury's orbit did. Newton's hypothesis finally ran into something it couldn't explain. But Einstein's theory of general relativity could explain it because his hypothesis includes the time it takes for gravity waves to travel. This explained Mercury's strange wobble during its orbit when Newton's hypothesis couldn't. So, starting from a couple of apples, Newton's hypothesis was such an incredibly powerful searchlight that it lasted for 232 years. So that's the way that searchlights work. You have to examine your evidence to tell how well your hypothesis explains your observations. The more scenarios it explains, the more it fits in with other hypotheses to explain more, the closer you are to having the best explanation. But before you assume you're right, you need to ask yourself some questions. Like, how far can you see with this searchlight? Does it make all of your relevant observations make sense or just some of them? What's still sitting beyond the searchlight beam? Is it because those observations aren't relevant? Or is it because your beam needs to be adjusted? Remember, this step keeps you from cherry-picking your data. But most importantly, you always need to look at and test other people's searchlights too. Don't get hung up on using a specific searchlight just because it's yours. At the end of the day, remember the goal is not to be right, but to light up the room. When you're evaluating deduction and abduction then, remember that the two questions you constantly have to ask are, how full is my bucket and how bright is my searchlight? When you're looking at these things, consider the size of the leap of imagination needed to make the connection between your observations and your inference or your hypothesis. Constantly check it against other evidence. Look at other possibilities that other people have suggested, and always ask yourself the question, what doesn't fit and why? Okay, that's it. I'll catch you around on the next video.